Guys, what's going on? So today we're going to be talking about an introduction to loop quantum gravity. This playlist is going to be focused on quantum gravity. So this playlist is a new playlist. We're going to be focusing first on loop quantum gravity, then we're going to move on to string theory, and then we're going to move on to more advanced areas and areas like M theory and this kind of stuff. So this is a large undertaking for me. This first video is going to be free to the public. For subsequent videos, I'm going to make this playlist a members only playlist because, again, this was putting this all together is tricky, takes a lot of time and effort. Also, a lot of the Patreon stuff is going to be also moved on to my YouTube account. I'm going to keep the Patreon page if you prefer contributing to this channel in that way. But because, thanks to you guys, I now have 3,000 watch hours for a while now, and I've decided to do something about it. So, without further ado, let's get right into loop quantum gravity, because I don't want to waste anyone's time on this. Okay, so we are talking about loop quantum gravity. Again, like I said, a lot of these topics are very esoteric, very abstract, but what I'm going to try to do is make things as non-abstract as possible by really going deep into things and really hashing out the concepts. I have tons of diagrams that I'm going to use in order to make things a little bit more succinct, a little bit easier to understand as well. So we're going to go through this slow. This is going to be a big playlist. Let's get to this. So we're going to begin our investigation of quantum gravity with the study of loop quantum gravity. The reason I'm choosing loop quantum gravity before string theory is because I feel like a lot of the topics in loop quantum gravity are a little bit more esoteric in nature. They're a little bit more abstract. They're a little bit harder to understand because we're going to go deep into the ADM formalism. We're going to try to understand holonomy. We're going to try to understand cohomologies and so forth. And so this is going to help us, I think, get a lot of the really abstract math out of the way. Then when we start talking about strings, hopefully things will be a little bit easier to understand. So in this introduction, this is a review of the foundational concepts of general relativity, and then we're going to sort of start hinting slowly towards a concept called holonomy or holonomy. So at the core of general relativity is the metric, which provides a coordinate basis for space-time. Okay. And we want to get away with relying on the coordinate basis. So we're going to use the connection as a foundational element of space-time. And so let's break this apart a little bit. So our traditional picture has always been, we have a manifold, and on that manifold, every point on a manifold can be regarded as Rn, right, depending on the dimension of the manifold. So if the manifold is 6-dimensional, right, every point on the manifold can be regarded as R6, okay? So if M was 4-dimensional, marker's a little bit thick, if M was 4-dimensional, then at every point in space-time, we can think of we can construct some sort of 4-dimensional system. In this or 4-dimensional Cartesian coordinate system. In this example here, I have listed a 3-dimensional, right? So M is a 3-dimensional manifold because we have 3 dimensions listed right here. But also within this space, this is a tensor, or this is a tangent space at the point P, which is what this TP stands for. It's a tangent space, and we'll see a little bit more in detail and more in a picture-like kind of way on what a tangent space actually is, because I want to go back to that just a little bit. But on this tangent space, we also have a metric. The metric is something that enables us to measure, excuse me, it's something that enables us to measure distances, right? So this metric tensor is given to us by the inner product in the tangent space. So if we have an inner product, we can create a metric in its own tensor space. This tensor space again is in this one in particular is a 0,2 tensor. So we have all our 0,2 tensors located in some space at point P. We can have as many tensors as we want in different types of spaces. So we can have one tensors, right? And this is sort of a review of general relativity. We can have many different types of tensors. These are all functions of space-time, right? So what this should really look like, this is kind of shorthand. What this Gij should really look like is Gij as a function of space-time, Ei, Ej, and those are the basis vectors. So this is the full-fledged form of the metric. The connection is given to us by derivatives of the metric. Okay, and so I'm not going to go into great detail on how we derive this. This is something that I derived at least twice, I think. One in my general relativity playlist, and one in my tensor calculus playlist. This connection tells us something about how objects accelerate, right? So physically speaking, we can talk about what how these things accelerate, or what these things actually mean in a physical sense. There should be a prime right there. And it does not, it's important to note that this thing does not transform like a tensor. Okay, this part is the tensor transformation part, and this part isn't. But because of this part, this newly transformed object is not that means it's not a tensor, right? And I'm realizing now there's a little bit of a weird notation going on here. This prime, put it here. This is just the new coordinate system. Okay. Again, this is all review. So I've gone over this before in my general relativity playlist. So if we assume that the connection is at the core foundational element of spacetime, we can then modify our understanding of the picture that we've been using so far. So the old picture was at a point in spacetime, we have a metric, and the metric, then once we take derivatives of the metric, we can understand the connection. The new picture is, well, at every point in spacetime, we have a connection. And what the connection is, again, is it's this thing that tells us how two vector spaces at 2 points in this manifold are related to each other. It gives us sort of this connection, if you will, between two vector spaces. Okay? And from the connection, we can calculate metrics. Okay? This is this new picture. We could sort of scratch out the metric now for when we're talking about loop quantum gravity. We're gonna skip, in this sense, just talking about the metric altogether, and we're really gonna want to focus on the connection, because the connection is the core foundational object here when it comes to understanding loop quantum gravity. Okay, so we're gonna put a pin in that for now, and we're gonna come back to it. So the connection tells us something about how vectors change as they're parallel transported to different points on the space-time manifold. When we're talking about fundamental objects, we're more interested in spinors instead of vectors. So let's review a little bit of spinor notation as well. Spinor dynamics is given to us by the Dirac equation, and here's the Dirac equation. Now, if you're unfamiliar with the Dirac equation, I would suggest looking at some of my Dirac equation videos on my quantum field theory playlist. And because again, I'm assuming you know at least a little bit of quantum, at least a little bit of GR, a little bit of calculus, right? And what I'm going to plan on doing in the next video is just giving a rundown on all the prerequisites, okay? Just to make sure we're on the same page. I want to give this video, though, you guys, as a little bit of free content to those of you who might be interested in perhaps contributing to the channel. So this is the Dirac equation, okay? We're starting here at the Dirac equation, right? Because again, this playlist could be as long as Everest is tall if we start from bare bones, right? So Dirac equation. Now let's see what we get out of this Dirac equation. More explicitly, the Dirac equation is a series of coupled differential equations provided to us by the gamma matrices. So the gamma matrices, these guys, gamma A, okay, are these guys matrices right here. And in this illustration, I'm really showing how these things are really coupled, right? So, and how they break down. So in this gamma matrix, we have portions that correspond to the matter fields, portions that correspond to antimatter, and then portions of each matrix that correspond to different momentum states for our particles. And then we have this identity matrix here to cap things off, right? Because when we look here, this is a series of matrices. Matrices, you need to subtract matrices from matrices. You can't subtract a scalar from a matrix. So in order for this to jive with this, we have this matrix for us as well. Okay, so in full matrix form, the Dirac equation looks like this, and I've highlighted all of the sort of physical correspondences within these matrices. Again, a lot of this is review. I'm assuming you know a lot of this, okay? You don't have to know it like in depth. I feel like you have to know, at least be exposed to this once before. All right, the Dirac equation predicts 4 possible solutions to this direct equation. I think I meant to write Dirac, but there's 4 possible solutions here, which represent 2 different particles, each with 2 possible states. Okay, and here they are, right? So we have electrons, we have positrons, and the electrons are going to be given to us here, right? So these are the matter fields, and then the antimatter fields are these guys. And I have their corresponding charges. So electrons have negative charge, positrons have positive charge, right? And they have a space-time dependence, right, which is given to us by this exponential on a space-time, right, x mu, with p mu as the momentum. And then it has spin dependencies. So the spin dependencies are a function of momentum, energy, and mass. Okay? And so compactified, this is what all of this looks like right here. All right? Okay, so we talked about the connection, we talked about spinors. Now let's move on to a little bit of parallel transport. So just like vectors on a manifold, we can imagine spinors on a manifold, and therefore imagine parallel transporting spinors, right? So this is going to take quite a bit of videos to actually understand what it sort of means to understand, or what it means to understand parallel spinors, because there's going to be a very interesting link between parallel spinors and holonomy, or holonomy, however you say it, and we'll get to that within subsequent videos. But this is a very core foundational piece that we need to understand here, and I'll be reiterating myself throughout this playlist, so that we can really sort of ingrain into our heads why this is so important. So recall that a vector is parallel transported when its covariant derivative along a curve is 0. To put it in another way, if we define V alpha as the derivative of gamma alpha, right, with gamma alpha being the coordinates in space-time, this is it's tangent to the curve, right? Because we understand that velocities are tangent to positions. We're just saying gamma is the positions, alpha is the velocities. Then the parallel transport equation becomes this, and we want because V alpha is parallel to our or is tangent to our spatial directions, this V sigma has to be its inner product has to be 0 with this covariant derivative. Okay. And so again, so we defined V sigma as V gamma sigma, and we can rewrite this whole thing, V sigma and D sigma, as here's our D sigma, here's our V sigma. This is really just, we can sort of, in theory, cancel those guys out and get D tau. Okay? And so what does this mean? This means that this piece here, right, so this is the derivative, this is a covariant derivative, but we can think of this as a total derivative, because this is just like a derivative, right? So this piece here is this d tau, okay? And then we have this extra piece here, which is why this is called a covariant derivative. Okay, so this is probably easier to see if I just highlight this in colors. This part here is right here, okay, which is what we get here. And then this part here is this here, because we defined that right here. All right. And then another color, just to distinguish a few things. This part here is right here. Okay. So this is our equation. Okay. This whole thing equals 0. And it's important to understand again that gamma are the coordinates, or space-time coordinates, and they're a function of some parameter along a curve in space-time. So this tau parameter, if we were to imagine a curve in space-time, this would be, and this curve is parameterized, right? So suppose this is tau 0, and that equals 0, and then tau 1 equals some number. So this, what this is telling us is that this is 1 unit of distance along the, and then because of the nature of curvature, tau 2 could be, say, right here, which is telling us that the distance here, say this was 2, is actually 2. And this could be just because of the nature of curvature, where some part of the curve is, the unit on some part of the curve is longer than another unit on some other area of the curve. Regardless, if we just clean this up a little bit, the point here is that curves are parameterized. This curve is parameterized starting at tau 0 to tau final, okay? And the coordinates on this curve are given to us by gamma. So this is tau 1, for example, and we can erect a coordinate system at tau 1, and that coordinate system again is given to us by gamma, and each basis, right, is a function of that parameter as well. All right. So the parallel transport for Spinor becomes this, and it's not quite obvious why I just sort of slapped a spinor in here, because this is and I'm going to go into this a little bit later. So we could sort of right now think about this as a vector. There's no reason we shouldn't be able to call this a vector for right now, because this really isn't that different from the equation we got up here, right? We're really just thinking of this thing as a spinor right now instead of a vector. Okay, but there's going to be an important difference between a vector and a spinor that we're going to come across later. I'm kind of just priming us for this so we can start getting this in our minds. Okay. And what I'm doing here is really just subtracting from both sides. Okay, subtracting this from both sides, and I'm putting an I here instead of a negative. Okay, instead of a negative sign, and for reasons of which that things will be a little bit easier when we start connecting a few other concepts together. But this is a coordinate system. This is a derivative in the coordinate system. And it's summing over these connections. This is the connection. And then here is the object that we're transporting, which is right here as well. Okay. So for now, we're going to see how to understand the solution to this equation, because right now you can really just look at this and you can say, well, I can actually come up with a solution to this. And the solution to this is right here. Now this looks intimidating. But remember what happens when you take the derivative of an exponential. When you take the derivative of an exponential, you just bring the exponential out and take the derivative of that. And you can see here that this in here is really just these two guys right here, right? So here's our connection, here is our coordinate system, and everything else stays the same. And you can see that when you take the derivative of this, when you take the derivative of this whole thing, well, the integrand is what's going to come out, right? So the integrand is what's going to come out, and we get this. Okay. So this is quite interesting, because what this seems to suggest is that this is a solution. Okay. What this seems to suggest is that the gamma is playing a role in being some sort of generator, because when we exponentiate a generator, then we get a transformation. Okay. The transformations that we all know and love, Lorentz transformations and so forth. So that's kind of weird, right? This this is a path ordering, and we'll get into what path ordering is later. We're going to review a little bit of the concept of Dyson series and what it means to path order. But for right now, we're just going to call this thing the holonomy. Okay, the holonomy takes us from, this is a parameter, right? So this here, the parameter I said here was tau. I'm just changing variable names because sometimes you'll see it as s. This is from the initial point in s to the final point. I can draw a picture. Here's our curve. Here's our s underlined, and here's our s overlined. Okay. I might interchange between different the nomenclature along curves of parameters along curves. So and I'll try to make that evident as we go through this series. However, this is our holonomy. So the holonomy is a path ordering of connections. Okay, it's a path ordering of connections, and it's the thing that's in the integrand. And a unique property of the holonomy is that if we take coordinate system let's say if we take a coordinate system from the initial point to some arbitrary point on the curve and multiply it by the coordinate system or the holonomy from here to here, right? So the picture that we're looking at is something that looks like this. Here's our curve, here's S, here's the other one, and then here's S, and here's gamma 1, and here's gamma 2. So this is H gamma 1, and this is H gamma 2. And so I'll just erase that. But the picture we're looking at here is something like that, or something like this. And we have this. So we're ordering the holonomy to get the overall holonomy. Okay? And it's quite easy to see that this satisfies the parallel transport equation. When we consider this solution, we're forced to realize that it looks like we are exponentiating what looks like to be a generator. Therefore, we can think of the connection as a generator for parallel transport. Okay? This is a very unique and interesting way of sort of understanding the connection. Okay? And so what we have going on, the picture that we have going on now is, so I just drew this curve up here. I've illustrated it right here. And so we're starting at some point along a curve. And as we travel along the curve, say we end up here, we're integrating over gamma and over the derivative of the coordinates. So we have derivatives of coordinates at each point in space and time. We have connections at each point in space and time. Okay. And these are coordinates because we have multiple of them, right? So if we go back to this here, alpha is going to run through 0, 1, 2, and 3. So alpha is going to run through 0, 1, 2, and 3, and 0, 1, 2, and 3 for alpha, right? And then we have our objects, right? Spinors, they're listed as spinors right now at these different points. But they can very well be vectors right now. Nothing is really stopping us from making this leap between spinors and vectors quite yet. But that's something we really want to focus on doing in the next video. So again, this is going to be the name of the game for quantum gravity. We're going to spend a lot of time talking about or breaking concepts down in many pictures. I love using pictures, and we're going to try to break things down as best and succinctly as we can, and we are going to try to understand things in a very pictorial way. And in the next video, I'm going to go over the sources that I'm using to put all this together for you guys, and this again will be for members only, because this takes a lot of effort, and I'm trying to create I really want to create something out of this. And so with that being said, I'll see you guys. Make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.